Today's lecture topic, we will continue on transfer functions, and also we will start some applications on Laplace transformation. As an example, how to solve differential equation techniques. Then next lecture we will continue on differential equation techniques and start how to solve some circuit analysis using Laplace transformation. So when we say now the Laplace transformation, there are many applications. I'm not sure, are you familiar with how to do differential equations using Laplace transformation? Yeah, we'll go pretty the same, but most likely we will use some signals or some mathematical expressions that we already invented in signals, like impulse function, step function, ramp function. So we will use this in addition to the regular expression equation that we know. Okay, so today is Wednesday, March 13th. The readings are from page 131 to 134, and it is the due date for homework number 9. So I expect everyone submit homework number 9. If you have any difficulties, or if you cannot make it, please let me know after that, at the end of this lecture. Then Friday, the readings will be between from page 134 to 140. Next week, our plan will be on Monday. The readings are page 134 to 140, and it's the due date for homework number 10. And you will see also due date for homework number 11 as well. But you keep in mind that homework number 11, you didn't need to submit. Do not submit. So problems and solutions are already posted on Canvas. So you just need to practice. Actually, this will be very important for you to practice for the test. Then in 20, Wednesday, it will be exam 2. Okay? Which will be next Wednesday. So most likely the exam will be covered from lecture, I think, number 14 until Monday lecture. So basically, anything in Laplace transformation, when we started from Laplace transformation until Monday lecture, basically mainly it will be about Laplace transformation, Laplace inverse, some applications like differential equations, transfer functions, and some circuit analysis. So most likely this week lectures are very important, and even Monday lecture also is important for the test. Because we learned before Laplace transformation, now we need to use this in some useful applications that we in this course. And most likely there will be tables, as we know, table 3.1, 3.2 in page 96 and 97. You didn't need to write any of this in your note card. You know you are allowed to have a note card. You didn't write anything because this will be provided to you in the test. Okay? And even some, we will see, I think in the next lecture, we will talk about some tables, some additional one table, I'm not sure, 1 or 2. But also that table will be provided to you. So when we go to this, I'm going to explore, tell you more about it. Now the transfer function, what's the transfer function? If I ask, what's the transfer function? We already discussed this last lecture. What's the transfer function? Yes?
It's a Laplace representation process.
Yes, it's the Laplace representation of the step response. Okay? So it will be h of s. And there is also another way to find the transfer function. Basically, it's the relationship between the outputs over the inputs. Outputs over the inputs of the system, and it will be in Laplace domain. Y of s over x of s. So most likely we will use Laplace transfer function a lot as a definition of the relationship between output over inputs. And when you go for future for control system course, you're going to use a lot the transfer function. So, and you will explore more and more about the transfer function and more applications about it. While right now we just focus more on the definition itself, but not the application, because the application will be in different process. So again, transfer function, relationship between the output over the input, and everything will be in S domain or frequency domain. Okay? Now, some comparison, or what's the importance of the transfer function, or the importance of T domain and S domain. So here, T domain or time domain. Then here, S domain, or in other words, frequency domain. In S domain, we used to say, like whenever we have input here, like X of T, output Y of T, and here is the system is H of T. So we used to say Y of T equals to the convolution. X of T convolved with H of T, right? While the best thing when we go to time S domain, here H of S, X of S as uppercase, all with uppercases, Y of S as uppercase, the convolution will be products. That's the nice feature, and that's why actually we are using frequency domain. That's why we will no longer use the convolution. We don't want to go to something that we don't prefer, something like will make a lot of troubles, which is in calculation problems. Some like a graphical tool will take a lot of time. Therefore, when we do the convolution, it will be much better. Do the S domain, it will be much better. So here, again, for the convolution, it will be like this, and of course, we will assume the system is coded. There are some other properties that we can use. As we know in the convolution properties, whenever we have H1 of T, then H2 of T, that was in time domain, we used to say this is equivalent to be H1 of T convolved with H2 of T. That's what we know from the first example when we discuss about the convolution. Now, how can we apply this into the Laplace transformation, or when we do the Laplace transformation? This will be as H1 of S, then here we have H2 of S. Then if we group them in one system, the good thing, the convolution will be products. So it's going to be as H1 of S times H2 of S. So again, when we do it with S domain, we will no longer deal with convolution. No more integrals, no more complicated things. Okay, does this make sense? Now some other properties, or whenever I say H1 of S, and here H2 of S, this is equivalent to be when I say H2 of S and H1 of S. So whatever we do first, it doesn't matter. And the same thing when we do their products. H1 of S, H2 of S, which is this type of properties. Okay? They are all the same, equivalents. Okay? Then that's some properties that we need to know about the transfer function, and also additional properties. So we used to say in convolution is distributive. So when we have H, one of T here, then here we have a sum. We can have a sigma there. Here is H2 of T. So we used to say in time domain as they will be added together, H1 plus H2. That was in time domain. The good thing in S domain, the same. So in S domain, here is H1 of S, H2 of S, then it's still like distributed. So when we make the sum, it will be the sum. This is equivalent to H1 of S plus H2 of S. Okay? Any questions? Now, since we know all of this and it looks like simple, let's discuss something important that we will use it. You will use it a lot in future courses, and even you will use it maybe even in senior design project, which is something related to feedback system. So what does feedback system means, and why this is important? Whenever we need to do a control, we need to have a feedback. Feedback like what? Imagine you are driving a car, and when you drive a car, you are pressing fuel and steering wheel, right? How you can judge that I need to press fuel or not? By monitoring the speed, monitoring the road. Is there any road hazard? Is there any problems that you see next to you? And also the steering wheel, you will locate based on your eyes, because most likely you will monitor the environment around you. So you have some sensors to measure the speed. You have the speed sensor for your car. You have also your eyes, so you can see any road hazard, any stop sign, any traffic lights, any crosswalkers, whatever, any other things that you see. Or also even like the road, sometimes there is a slope of the road. So all of those are sensors. So your eye is sensor, your speed meter is sensor. Then what you're going to do, you need to take an action. And this action is based on what you see, based on the measurement. So this is like a feedback. Or another way, as example of the feedback, which is basically when you submit your homework or an exam, and they all say like your grade is, for example, 90. So we need to say, okay, how can I get 90? I think I did pretty well, I did good, so I should get 100. So that's why I'm returning this to you, then you will see, okay, you will see the grading, right? When you see the grades, this is a feedback. Then you will learn from your mistakes, then when you go to the final, okay, I'm gonna avoid this. This is something we call it, you will do something positive or use the feedback that you've learned to correct yourself. So we apply the feedback everywhere. So basically, again, you can have an input. Let's assume like the car. So you need to, for example, control the car speed. Okay? So basically, what you're going to do with the car speed, you will control, which is the car control, car speed control. By pressing fuel or not pressing fuel, which is, our steering wheel. I'm here, I'm just going to assume like the speed, so which is pressing fuel or brakes. So I'm going to write it as control. Then, what you are actually controlling, the car speed, so there is a car body, okay? After that, this is not enough by pressing fuel and or pressing brake without recognizing what's going on. This looks like I'm walking as blind. You cannot see anything, right? You need to have a feedback. So that feedback comes here, the output here is speed. You need to measure the speed using the sensor. That sensor will be used to measure the speed. Then that speed, when you see the speed meter, then basically you will determine that, okay, my speed now is 80 miles per hour, and to reduce my speed to be 70 miles, or 60 miles, and make it 70 miles. Then you need to take an action. So you need to have your reference speed. So you have reference speed. That's my reference speed, which is 70 miles per hour. Then you have the speed that you already measured from the sensors that you have, which is 60 miles per hour. So what you need to do, what's the difference? 10 miles per hour. So you need to press more fuel to remove that error, which is 10 miles per hour. Therefore, how can you monitor that your speed is within your reference or not? Then you need to subtract plus minus to get the error, speed error. Then it will go back to your controller. So your target is to make the error as low as possible, to make it 0. That's my target. So the same thing when you do the cruise control. When you press the cruise control, set speed 70 miles per hour, your current speed is 60 miles per hour, then the cruise control basically will monitor the speed. We have the sensors. Then it will basically do the cruise control will press more fuel until making the error 0. Then it will go maintain a constant speed. Okay, that's an example with the feedback system. And the feedback system again is very important, and we are using this a lot in our daily life. All of our life is on feedback systems. That's how I can walk, that's how I can talk, that's how you can hear, that's how you can learn everything in the systems, car systems, even in the air conditions. You have the air conditions, for example, assuming the temperature is, you set it as 70 degrees, the current temperature is 65, then the heat will be on until reaching the 65, until reaching 70. How? The heat will be on and keep monitoring until reaching the steady state error or until reaching the error to be 0. And you will learn more and more about this in control system class. But here just like as an overview about the feedback systems and the importance of this. Now, I'm going to give you like a demonstration in signals. So now, let's go more in math other than like the concept. Because again, you will learn this later in control system class. So assume we have x of s. Then here we have f of s. F of s can be the car with the controller, whatever. So I'm going to assume it as a function. Then the output is y of s. Then we have a feedback system g of s. Well, mainly will be the sensor. It can be some other systems as well. It can be maybe a feedback, because if there's some other road hazards, we need to take an action, like adaptive cruise control, which is basically not only the speed, not only measuring the speed, also we need to take into consideration some road hazards, or which is the distance between other cars, and etc. So we have g of s. Then basically, I'm going to assume here is positive, here is negative. Yeah, this is pure signal or pure math. This is not, I'm not talking about the practical things here, so it can be sometimes the sign, positive, negative, negative, positive, 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 whatever. In this example, I'm going to assume this as positive. And the flow, of course, from the inputs to the outputs, that's the flow. Now, we need to find the transfer function. And again, you're going to use this a lot in control systems. So how to find the transfer function with this? Basically, what do I mean by finding the transfer function? I need to model this, convert this system from complicated one to be like this. So here this will be as y of s, here is x of s, and this is h of s, the transfer function. So the overall target is, yes, we have a feedback system, but I need to convert this to be like this by relationship between output over input, and that's it. So I can avoid the confusion of the complexity in this graph, or this is something we call it block diagram. This block diagram, as you will learn later, going to use a lot in electrical engineering. Then our targets, how to find the transfer function to make it only the relationship between outputs over inputs. How to find this? That's the way that you need to think about it. Then assume here, this is y of s, right? Then look at the arrow. Here it is y. After g, it will be y times g, right? Y of s times g of s. This is x of s. Then here, what do we have? After this sum, it will be x minus yg, right? So what will happen to y? It will be x minus yg times f. Again, in summary, what are we? This is y, okay? Y goes here. Then, since we have g's like a product, y times g, okay? Then we have a negative, so negative y times g. Then we have x, so x is positive here, or plus, and this is minus, so x minus yg, okay? All good? After that, since my target, I need to go back to 1. So it will be x minus yg times f. Because here this is a product, then I'm back to 1. I'm trying to go through a loop. Start from y and go back to 1. So we end up having y is actually the same as x minus yg times f. Okay, does this make sense? Now I'm going to write this formula here. So we end up having y of s equals to x of s minus y of s times g of s, all of it times f of s. Okay? Our target is to find the transfer function. The transfer function means the relationship between output over inputs, which is y over x. So since we have y here, we have x here, we need to figure out a way that isolates y alone on one side and isolates x on one side. So then let's do the product. So it will be here y of s equals to x of s times f of s minus y of s, g of s, f of s. Move this to the other side, then take y of s as a factor. It will be as 1 plus g of s, f of s equals to x of s, f of s. Okay? Does this make sense? Now, we need to find the transfer function, which is y of s over x of s, which is going to be f of s over 1 plus g of s minus f of s. And this is again h of s, which is a transfer function, then prop them back. Okay? So therefore, I can say I'm going to replace that system that I draw. So here we have x of s, here we have y of s, then it will be f of s over 1 plus g of s. Does this make sense? Now let me give you a few seconds to write, then I'm going to go an example, quick example about this. So example, assume we have x of s, then here's the sum, here's the subtraction, then we have 1 over s plus 1, 5 of s, and the sensor feedback is 1 over s. Then we need to find the transfer function, find tf as a shortcut transfer function. Or sometimes we call it h of s, whatever. So how to follow this, here I'm going to make a slight change, I'm going to make it positive. So it's not every time negative, sometimes positive, sometimes negative. You need to take this into consideration. So what I'm going to do, the best thing, I can call this block as G1, I can call this block as G2. So you can follow with me. So here, this is y, this is y times G2, this is x, so that here it's the sum, so it will be x plus y G2, then y will be x plus y G2 times G1. Okay? Does this make sense? Now let's substitute them. So here, we already agreed that y of s equals to x of s plus y of s, g2 of s times g1 of s. So, does everyone know how we get this? You want to explain it? Re-explain this, or is it clear? In summary. start from y. Here's y. Here I call this g2. So this is a product, y times g2. Then here we go as with the sum. Then here we have x. X, because it's positive, positive x, here positive, positive, y g2. Then there is a product, so times g1. So x plus y g2 times g1. That's how we get it. Okay, now, we need to find the transfer function. So let's try to find the transfer function, then we can substitute g1 and g2. So to find the transfer function, y of s equals to x of s, g1 of s plus x of s x of s, g2 of s, g1 of s. So let's try to find y of the transfer function. Let's see, here this is 1. Okay, so it's 1. Then let's put y to the other side, y of s minus y of s, g2 of s, g1 of s equal x of s, g1 of s. Then take y as a factor, 1 minus g2 of s, g1 of s equal to x of s, g1 of s. Then the transfer function h of s equals to y of s over x of s, which is going to be as g1 of s over 1 minus g2 g1. Substitute g2 and g1. g1 is equal 1 over s plus 1, g2 1 over s. 1 over s plus 1 divided by 1 minus 1 over s plus 1 and 1 over s. Okay? Now, we can make a product each term by s plus 1, here s plus 1. That's what we do. Then basically, it will be converted to be s times s plus 1 divided by s times s plus 1 minus 1. Then let's do simplified more. It will be s squared plus 1 over s squared plus s minus 1. And actually here, s squared plus s. S times s squared plus 1 times s. Then this is h of s. Okay? Does this make sense?
Why wouldn't the numerator just not be s?
Oh. I think I messed up this. Let's see. I messed up this. Let me do it again. So here, when we make the product, s plus 1 equal. So it will be here s divided by s plus 1 minus 1. Then it will be s over s squared plus s minus 1. Now it replaces. So since we find the transfer function, then we can use it later, use it for the control class by making the applying the PID controller, doing some closed loop analysis, etc. So you will learn it. But here, what you need to know about the feedback system is like what we discussed here. Yes.
How did you get y of s equals g1 of s?
Where?
In the transfer function right here, you said y of s numerator.
Yeah, y of s over x of s.
That's not what you get. It's g1 of s.
So here is y of s, here is x of s. Divide by x of s both sides, so it will be y over x. Then divide by 1 minus g to g1 both sides. Any other question? let's go more about the block diagrams. So some block diagrams. So we have x of s like this. Then we have something we call PO. We have summer. Then we have 1 over s B1. So you plus. Then here is another sum plus here y of s. Then we have 1 over s. Then we have minus AO. Then subtract. So now with this complicated or block diagram, before making analysis, I need you just to make sure to understand what does each symbol mean. So whenever you see here, like look at the arrows, also the arrows are important. So whenever you see like this box, it is multiplied with a constant. And just multiply it as a product. So it will be like, since here x, it will be like x times b. And whenever we have also this box, it is multiplier as well. But keep in mind, this is considered as ideal integrator. 1 over s is the root integrator. Then here, since we have this one, this is called adder, which is make the edge of summer to make sum of these segments. So how can we solve this type of circus to find the transfer function? Every time when we say find the transfer function, we need to find the relationship between inputs, outputs. Then basically, we need to model all of this to be only like input over output. So here is x of s, y of s. Now, how can we model it? Since we have two different loops, I encourage you to do each loop by its own. So this will be loop 1, I can call it as h1. This is loop 2, and it's h2. When we have multiple loops like this, the best way to deal with this is isolate each loop alone. Okay? And in the middle, we will have some intermediate variable. And that's intermediate variable, I can call it as z. Okay? So, what should I do? Make a transfer function. Again, we will try to isolate it. Make a transfer function for loop 1 by making z of s over x of s. Then make the transfer function of loop 2 by making y over z. Then after that, multiply it together. So basically, the procedure we will say is to find h1 of s, which is going to be as z of s over x of s, because the outputs is the intermediate variable, while h2 of s equals y of s over z of s. It's like cascading, because the output of loop 1 will be input of loop 2. Okay? Is this clear? This is loop 1, loop 2. The output is z. This is the output of loop 1, which is going to be the input of loop 2. So z of s will be the input of that. Then we need to find for each loop the transfer function of each loop. After that, we can say that h of s is actually h1 of s times h2 of s, the product. How can I validate this? Which is going to be as z of s over x of s times y of s over z of s. Then z of s and z of s will cancel each other, which is going to be as y of s over x of s. That's how we figure it out. That's how we find it. Okay? Does this make sense? Now here I'm just telling you how to find the way, that's how to plan to do our answers. Then I'm ready to do the analysis. So let's do with loop 1 first. Look at loop 1. Loop 1 here is x, so this one will be x over s, then x times b1 over s, then here x b0, then they will be added. So z will be x times b0 plus x b1 over s. Okay? That's what I'm going to do. So I will say for loop 1, z of s equals to x of s, or b0 times x of s, plus x of s times b1 over s. Okay? Then I need to isolate output over input, so I can take x of s as a factor. Then we will say z of s over x of s equals b0 plus b1 over s. That's the first one done, which is this is h1. There is no feedback on it, then we'll make it much easier. So I just basically I wrote it in terms of s values. Now the first one done. Is this clear? Let's do the next one. To do the next one, we have a feedback. So keep in mind here is z, here is y, then this is y over s, this is negative a y over s, then here since we have negative, then it will be here z is positive plus minus the negative of ax over s equal to y. Therefore, we can say z plus ax over s equal to y, equals to y. Something is y. Again, this is a feedback system. This is y. Again, here is water. It should be water. Here is y. Now y multiplied by s, y over s, y over s. Then y over s, there is multiplied by negative a0, y over s. Then we have a negative here. So z, it becomes positive, z is positive. Then minus, because of this negative sign, then we have the other negative sign of this. So minus negative a y over s, so minus minus will be positive, so it will be z plus ay over s equal to this. Plus a0y over s equal to this. Then I can write this down. So we can say y of s equals to z of s, minus minus will make it positive, so it will be plus a0 over s y of s. Okay? Move y of s to the other side because we need to isolate output or input. Then it will be y of s minus a0 over s, y of s equals to z of s. Therefore, take z of s as a factor, y of s as a factor, and divide by z of s. It will be 1 over 1 minus a0 s. Then this will be called h2 of s. Okay? Does this make sense? Now, we just calculated h2 of s. Remember, our target is to find the total transfer function. So the total transfer function, h of s equal h1 of s times h2 of s. So h1 of s was b0 plus B1 over S times H2 of S, which is 1 over 1 minus A0 over S. Okay? So I'm gonna multiply by S on both sides. So I'm gonna multiply by S here, S squared over S squared, something like that. So basically I'm trying to, let me see, S squared, or S over S. Let me try S over S first. So it will be as B0S plus B1, all of them divided by S. That's S over S. Then the other one, which will be S over S minus H2. Okay? Does this make sense? Then let's do more simplification, which is going to be as B0S times S, B0S squared plus B1S divided by S squared minus A0S. This is H of S, which is again the relationship between output or input. Okay, is this clear? Any question? Now I'm going to just go another topic about using this transfer function, which is called stability. System stability. So we already mentioned about stability, stable system before, but now we're going to use system stability using transfer function. So basically, we already did how we convert the block diagram into a transfer function. And system stability, when we have X of S, then H of S, this will give us Y of S. That's the flow. So how we find the stability? Look at H of S, which will be numerator denominator. Then look at, here we have zeros, we have poles. So look at the poles. Most likely the poles S will be real parts plus J imaginary parts. Or in other words, we can call it sigma plus J omega. Which determine the system, is it stable or not, by looking at the real parts. Real parts of the poles. Then there are three cases for stability. If all real parts of poles less than 0, which is negative, in other words negative, then we can say the system is stable. Then, number 2, if at least one pole with real parts larger than 0, then the system definitely will be unstable. Okay? Then number 3, if at least one pole with real parts equal to 0, this will be called marginal stability. Okay? So basically, the stability can be determined by looking at the poles. If all of the poles, the real part of them, are negative, then the system is stable. There is no problem. If the system, one of the poles located at zero, with zero real parts, then it's marginally stable. If one of them more than zero, then it's unstable. Yes?
But if you have one pole that's positive, one pole that's zero.
The positive will make it unstable. So that's why I say at least one pole. At least one pole. At least one pole. While in order to say the system is stable, of all poles, all real poles, all real particles. So if all of them negative, then it's stable. If one of them equal to zero, this is marginally stable. One of them positive, then this is definitely unstable. If that's one, if two or three, of course, unstable. But I mean, when you detect one of them, make it larger than zero, then definitely will be unstable. In other words, we can say the poles, all of the poles must be on left half plane. Because we know the S node here is sigma, here is omega. So if all of the poles here, this is stable region. While this region is marginally stable. Then this region is unstable. That's how we understand this. Make sure the poles are located in the right, in the left, not in the right. Example: we have h of s equals to 1 over s squared plus 2s plus 3. Define stability. Or find stability. Basically, you look at the poles, so find the roots of this root. S squared plus 2s plus 3 equal to 0. After doing the general formula, the general quadratic quotient formula, it's going to be complex number, so it's going to be negative 1 plus minus j square root of 2. Again, our target is to look at the real parts, don't look at the imaginary, only the real parts. Now, real parts here is negative. This means what? Stable. Okay? And the left half plane rule on the x1 plane rule, so you will see here is negative 1, here is j square root of 2, negative j square root of 2, and the intersection is here, the intersection is here. Okay? So those are the location of poles here and here. Since then this will be on the stable region. Okay? So that's what you need to know about the stability. Later in the control system class, there's a chapter about the stability, which is how to determine the system. Is it bounded in or bounded out? It's stable? Is it asymptotically stable, marginally stable? But here, so far, you need to know like about the location of poles will determine the system is it stable or not. Other than when we go use the time equation, bounded in or bounded outwards, and make that a cheap stability, we can do this differently. Okay, so I didn't have enough time to go to the differential equation, but just maybe we'll discuss this in this lecture, but I'm going to just write, which is solving differential equations with Laplace transformation. I encourage you to look at page 114, 117, and also keep in mind these two properties in table 3.1. The first derivative, dx by dt, equal s x of s minus x of 0 negative. Then the other property for the second derivative, dx of t by dt squared, here in Laplace transformation. This is going to be s squared x of s minus s x of 0 negative minus x bar of 0 negative. That's what we will discuss more next lecture, which is how to solve the differential equations, like differential and differential equation course.